There we go. Creepy screen. Hi, everybody.
Hello.
Hello. Everyone's here, talkative. Happy Thursday. One more day till Friday. Friday, yes. Indeed. So, let's see. I don't have your quiz ready yet, but that will happen after class. And I don't have your homework ready yet, and because I keep talking and not actually finishing lectures when I thought I would, I pushed your first homework back 2 days. So it is not due, so note that I changed the dates in week 4. This is Tuesday, Wednesday, Thursday of that week. It's going to be due Wednesday night rather than Monday night. That way we have one more class before you'll be turned loose on it. And I'll let you know as soon as that is up. We're going to talk today about the stuff that you get to practice in homework 1 and as well as next time. So I sent you an example. It's eventually going to have 2 parts to it. I'm not quite done with the second part, so example part 1 is enough for our first homework, so that's what I sent you, and we've got lecture 1. Yeah. Everyone figured out homework 0. We're all got that running to go, so everything should be fine. All right. You want to jump in? Yeah. So since the timing of this is such that some of this will be redundant with what we just talked about on Tuesday, so I don't have to spend a whole lot of time, but the focus here is to start with binary outcomes. How do we predict them? And then how do we predict categorical outcomes? And very strongly related to how we predict binary outcomes. So this is lecture 1. By the way, I changed the numbering system that goes with your lectures and examples and stuff. So lecture 1 and example 1 go with homework 1. Lecture 2 and example 2 go with homework 2, like to try and make it easier. That's why what we've been doing is lecture 0, because it didn't have a homework that went with it. And we'll get all the way up to, if we get everything done that's planned, lecture and example 7, which does not have a homework that goes with it. So that'll be what we do the last week or 2 of class. So, all right. I don't think we have any Zoomers here today, but I'll keep, it'll shut off automatically, so I'll keep it open whenever I start class just in case anyone is connecting that way, but if not, here we go. All right. So this thing, we talked about this last time, but here's some more details. How these models differ from the general linear models that you already know. What has to change in order to be able to predict a non-normal outcome? That's the idea. In a slightly different order, focusing on number 1 here, the conditional distribution of our outcome is going to be something that's not normal. So what does conditional mean? It means left over. It means for the outcome variability that is left after accounting for predictors. That's what conditional means. So general linear models use a normal conditional distribution to describe the y variance that's remaining after prediction. We call that residual variance. And one thing about the normal is that that is a separately estimated parameter. The normal is one of the few distributions in which the mean and variance are 2 completely unrelated things. Almost every other distribution that we're going to work with this semester, the mean and the variance are related to each other. Either they're the same or in other ways determined by, the mean determines the variance. Why do we do this? Why does it matter what kind of conditional distribution we pick? Well, we want to pick something that's plausible for the type of outcome that we have. It should try to match the same family. Had a series of questions after class last time. Who was that was talking to me about this? You don't know what conditional is until you have a model, right? So some of these, it's going to be obvious what the right distribution is. For instance, binary data, it's going to be Bernoulli, the end. You can't get that wrong. That's the only possible one. Other types of variables like counts, there's maybe 4 or 5 different ones that you could choose from, and it won't be obvious necessarily which one is which. But you want to pick something that's more plausible. The reason we care, standard errors. Standard errors come from variance. If we don't have the right model with respect to variance and how it's either related to the mean or not, we don't have the right standard errors, which means we don't have the right p-values. So it's the inferences that we're trying to predict in this case. This, if you're reading along in the Agresti textbook, this aspect of the model is called the random component, meaning the error portion of the story. So that's number 1. We're picking something other than normal. What we pick is based on the type of outcome values that are possible for that variable. Number 2 is a link function. In notation, it will be written oftentimes like this, G, sometimes it's H, but a dot like that. The key idea of this link function is that it is a transformation that takes an outcome that is bounded and not continuous, and it turns it into an outcome that is continuous and unbounded. You are not transforming the data. If you're going to predict a binary outcome, the outcome variable that you feed into SAS or Stata or what have you is the original column of ones and zeros. We're not transforming data. What happens under the hood is that the outcome to be predicted is the linked function version. If you want to go back to the original scale of the data, that's known as an inverse link. And what happens when you go back is that the predicted outcomes stay within the boundaries that they're supposed to have. So for example, if I have a binary outcome, the mean of a binary outcome is the proportion of cases that have a 1, right? That's the thing we're trying to predict, is a probability of a 1 for any case. And we put in predictors that will bump that up or down based on the values of the predictors. Well, probability is bounded. It ranges continuously between 0 and 1, but it can't go below 0 and it can't go above 1. So we need to have some way of predicting an outcome that doesn't have those problems. And there's something called a Logit, our new best friend starting today, that solves that problem. Another example of a link function that's very common is the natural log. So by the way, in this class, when I say log, it's always natural log. It's not base 10 or any of the other kinds you could possibly have. It's pretty much always that way in statistics. If you're predicting a count type outcome, or anything where 0 is the lowest it can be, the log works really well because log values can go into positive and negative infinity, but when you unlog them back, or exponentiate them, as it's technically called, then the predictions stay above 0. So those are the main two that we'll see throughout the semester, the Logit or one of its cousins, and the log. By the way, the reason that GLM sometimes stands for general linear models and sometimes stands for generalized linear models, that's not confusing at all, right? The reason is that the general linear model is a special case of the generalized linear model, where the link function that's being used is called the identity link. Do you know what that means? Y times 1. That's the link. As opposed to y that gets logged or y that gets logited. Y times 1 is an identity. So a general model is a special case of a generalized model. So generalized is the broader term. The third part then, this is the part you already know. This is the linear predictor as it's known. I will note that in multi-level data, this includes both a fixed and random effects. We're not having random effects until later in this semester when we get to multivariate data, so it's just fixed effects for now. But the good news is that if you're predicting the link transformed outcome, you can talk about intercepts and slopes the same way that you already know. Like the intercept, expected outcome when y is 0, right? Right? You know that one? Well, now it's not when y is 0, when the linked y is 0. So it's when the logit is 0 or when the log is 0. But 0 is still the basis of an intercept. The slope, same idea. Change in y per unit change in x. It's change in logit y or change in log y. But then everything works the way that it's supposed to. You can test main effects, you can test interactions, you can have nonlinear effects of quantitative variables, you can have categorical variables and dummy codes between them, you can have any of that stuff you already know how to do. That's all the same. In terms of estimation, there is no longer a simple set of formulas by which the slopes fall out. So in general linear models, there's this thing called x transpose x inverse x transpose y. Like that's the matrix version that says what the slopes should be no matter what. There's no analog to that in these models. So the estimates for the intercepts and the slopes for the fixed effects have to get found iteratively the same way as any sort of variance-related parameter. So that means the more things you have in the model, the longer it can take to estimate, and the more likely you are to run into estimation problems in that case. That doesn't show up much in single-level data. It shows up more often in multi-level data where you have fixed and random effects at the same time. So let's see how this plays out for one type of outcome, binary. So what I'm talking about now, other people would call logistic regression. That's what this is called. So if I have a binary outcome, what I'm trying to predict for each person is the probability of a 1. That's my conditional mean. So note there's different scales here. The original variable is just zeros and ones. The conditional mean is a probability that ranges from 0 to 1. So the conditional mean has more possible values than the outcome. That will be true for other conditional mean types as well. So let's say that you didn't have this class. You did what you knew was the most right thing to do. Has anyone ever done a data analysis where you look back on it and go, oh my God, that was so wrong? Yeah. Truth, one of my favorite papers that I wrote as a postdoc, the data for it, the whole story behind it was my master's thesis that was a complete pile of crap. It was unpublishable for the reasons that like you were supposed to have made some sort of contribution, but I used it as a great example of when you don't use a repeated measures ANOVA for something. And I took it apart and turned it into a cross random effects model. So yeah, I can give you a whole list of publications where I now know something is wrong, that I know better. So if you're feeling bad about that, don't, because it doesn't stop. Science is self-correcting, right? Like all we can do is do better next time. But let's say that I'm someone who hasn't seen any of these models. I have a binary outcome, and so I want to run a regression on it, right? Sure, why not? So I might have a model that has 2 predictors in it. So the probability of a 1 for each case is a thing that I'm predicting. I have an intercept beta 0, so that would be the expected probability of a 1 when my predictors are 0. I've got my slopes here. That's the change in the probability for a 1 unit change in each x. Cool. Then I've got E, which is the difference between the probability that's predicted by the model and my actual 0 or 1 value. Okay, so what could possibly go wrong? Well, let's start with the model itself. When you put x1 and x2 in here, you're saying linear relationships. So this is the picture that I showed you before, the idea that you can't have a linear effect of a predictor that goes on forever and ever. It doesn't make sense in terms of predicting the probability of a 1. Probability has to shut off. So we need to find some way to tell the model that the predicted outcome cannot go past 1 or 0. We need to find some way to take the slope and sort of like squish it to make it fit. The way that that happens is your link function. There are 4 different ones that I have heard of for binary data. There's probably more out there in the world, but I'll give you the 4. One of them is by far the most common, and that is our new best friend, the Logit. So here's how this works. Step 1 is to take the probability of a 1 and turn it into something called an odds. So we have the probability of a 1 over the probability of a 0. When we have more than one ratio of those, it's an odds ratio. But the scale of odds is weird. The scale of odds goes from 0 to positive infinity, and it's asymmetric. So for instance, if the probability of a 1 is 0.7, then the odds of a 1 is 2.33. That's if you stick 0.7 in the numerator here and 0.3 in the denominator. If you flip it around, then the odds are 0.4. So you can't necessarily look at one odd and make a good intuition as to what the opposite would be. It's asymmetric. Where everything where probability is less than 0.5 is shoved between 0 and 1, and everything where probability is more than 0.5 goes from 1 to positive infinity. It's a weird scale, and I hate it, quite frankly. Hate. But some genius figured out that if we take the natural log of that thing, then we have a scale that we can work with. It's centered at 0. It goes on to positive and negative infinity in a continuous fashion. And this is our friend, the Logit. I call it Logit. I got into an argument with a former grad student. Hello, Ryan Walters, if you're listening. He has a real job now. He's probably not, but maybe some of his kids are. He argued with me that this is a logit because you take the log and you log it. See, it's a logit. The rest of the world says Logit. I've also heard Logit, which is another variant. I don't care which one you say. It's up to you, but I'm going to say Logit. So this thing is symmetric, which makes it a lot easier to work with predicting the 1 or the 0. So if I have a probability of a 1 that's 0.7, that corresponds to a logit of 0.8, 846 specifically. If I want to talk about what the probability of a 0 is, I throw a negative in front of it. So I immediately know if I have what my logit is for a probability of a 1, I can go the other way. And this works out to be advantageous in software because some programs predict the probability of a 0 and some of them predict the probability of a 1. And it boils down to a difference in sign. So the mapping of the probability scale to the logit scale is shown here, where 0 for logits corresponds to a probability of 0.5. If you go up to a probability of 90.9, that corresponds to a logit of 2.2. If I go the same distance relative to a probability of 0.5 down to 0.1, that corresponds to a logit of negative 2.2. Probability of 0.99 goes to a logit of 4.6. Can you guess what the complement would be? Probability of 0.01 is a logit of what? Negative 4.6. So you will see logits that range in theory from positive to negative infinity. Most programs have some sort of cap. So for instance, M plus cuts off anything after 15. The highest the logit can be is 15. If it tries to come up with something and it can't figure it out, it's like 15, that's it. Because it's closer and closer and closer and closer to 1. But the logit is actually undefined at 0 or 1. So it's approaching, that sort of idea. So here's a plot that I like that illustrates the fact that this is a nonlinear transformation of probability. On the top is probability. The mapping of distances in probability to distances in logits, logits is on the bottom. So if I go from a logit of 0 to 1, that's a bigger shift in probability from 0.5 to 0.73 than if I go from a logit of 1 to 2, which is 0.73 to 0.88, than if I go to 2 to 3, and so on. So the benefit of this logit land is that you can have a slope that goes on forever and ever and ever in logits. But when you do the back translation, what I call an unlogit, which is actually the inverse link is what you're supposed to call that, the probabilities stay bounded like they're supposed to. So in terms of neutral points on these 3 different scales, a probability of 0.5 corresponds to an odds of 1, corresponds to a logit of 0. And people will write out this model as predicting one of those 3 things, and that's why the model looks so very different. This plot right here, the way that I made this plot is to generate a slope of 1 in predicting a logit, and then unlog it, and that's what it looks like. So when you back translate a 1 unit change in logit to what it works out to be in probability, it takes this S-shaped curve right here. So have you seen this kind of thing before? Not in logits, but like earlier in statistics? Does this sound familiar? Fisher, yeah. What are you thinking of? Say it one more time.
Just make transforms that make it not meet the 1, 0, but approximately.
I think you're going somewhere different than where I thought you were going, but it's possible you would have seen this. How do you make a standard error and a confidence interval for a correlation? Anyone remember that? Fisher something, that's where I thought you were going. Z, Fisher Z, do you remember that? Fisher Z is a logit-looking transformation. It takes correlation, which is bounded between -1 and 1. It converts it to, he called it Z, even though it's not a Z-score, it's like a different Z. That's unbounded. Then you figure out what the bounds are on that, and then you back engineer it into a correlation again. So it's the same concept that shows up here. This is our friend the logit rather than the Fisher Z transformation. So The Logit, our new best friend, solves the first problem that we have, that these slopes for a 1 unit change in x, they're talking about a 1 unit change in the Logit. That's what they're going to talk about, because the Logit can go on forever and ever. So that part's fixed. What isn't fixed is the standard error for those slopes. So if I'm back here using a general linear model to predict a binary outcome, then I'm saying the residuals of my binary outcome are going to be normal and have constant variance. But if my actual outcome is either a 0 or a 1, my residual, how far off each observation's actual y is from the y hat that's predicted for them, then it's either going to be 0 minus the predicted probability or 1 minus it. So at any given level of probability, you can either be off in one way or the other. There's only two kinds of residuals. So the residuals can't be normal because there's only two possible values for them. And those two possible values, the variance is dictated on where you are on the probability scale. The variance around a predicted probability is the largest if the predicted probability is 0.5. It shrinks as you move away from that. That's the definition of non-constant variance. So standard errors for these things that don't understand that the variance needs to shrink in conjunction with the predicted probabilities, those are going to be all messed up. So how do we fix it? We order a new kind of sandwich, right? Pick a new model. Rather than saying our residuals are supposed to be from this normal distribution, we say they're from our friend Bernoulli. Bernoulli has only one parameter, p, the probability of a 1. The likelihood function for it, the formula by which height is calculated. Remember height? The best answers are the ones that make everyone's data together as tall as possible. And you can compare that height under one model to a height under another model and see if it's taller, that kind of idea. So it's the parameters that get spit out are the ones that make the height as tall as it can be, and then we can judge other models the same way. The likelihood function is the simplest one of all. It's the probability of a 1, if that's what you got, times the probability of a 0, if that's what you got. The end. That's height. I have within lecture 0, part of the Excel spreadsheet that I got out. Let me show this one to you. I made a tab for the Bernoulli. It's opening Excel. It's thinking about it. So Bernoulli doesn't have variance as a parameter. So here's normal. We did this one. Binary is the next tab over. So I have 10 cases here. Some of them are 1s or some of them are 0s. It works out that 6 of them are 1s. That's the mean. Here's the height of each observation. It's the proportion of, it's the probability of a 1 if that's what you got, times the probability of a 0 if that's what you got. Thank you for killing my Zoom link. That's fine. No worries. And the mean is the one that makes everybody's data as tall as possible. So in comparison, if I try to say, no, the mean should be 0.8, well, it makes some of the people's data taller, but not everybody's. So it's the same principle. It's height, but it's height calculated with a different formula. And in order to calculate height, you only have to know the probability of a 1. You do not have to know variance because variance is determined by the mean. And you can do this in SAS. Let me find the output for that. So I did normal, and then I did Bernoulli as the next one. And that number right here, it's -2 times the height. From an empty model, just reading in those 10 observations, that's the exact same number I came up with here. That's where it comes from. Finding what the best answers are when there's a lot more parameters is trickier and not something you can do in Excel. But the concept of height still holds. It's just height and a different metric. Because, by the way, the heights are in different metrics, you can't compare them. So like the log likelihood height from a normal distribution, you can't say, oh, that's bigger than the one for the Bernoulli distribution, so that must be better. That'd be like saying I have more inches versus centimeters. Like they're not on the same scale, so you can't compare them directly. So if we swap out the Bernoulli distribution, then it understands what the possible distribution of the residuals can be. The only catch is that there's no more residual variance. So all of the things that we rely on related to residual variance, like R square, and this distribution, it's gone. There's pseudo R squares, there's various attempts at it, but they're not exact values the way they can be in the normal where variance is a separately estimated thing. Okay, how are we doing so far? So we're switching our model in two ways. We're predicting the logit, the log of the odds of a probability of a 1. We'll get practice in saying that. Ready? Say it with me. It's the log of the odds of the probability of a 1. That's my friend the logit. We do that so that we can predict an outcome that goes on forever and ever. When unlogited, the inverse link, going back to probability, stays within the bounds. Then we say E isn't normal, E is Bernoulli, problem solved. Now, what does the model look like? Because you can express the predicted outcome in 3 different scales, logit, odds, or probability, the model looks different. And this is one of those things that makes this much harder than it needs to be because different people in different fields will pick one of these 3 and talk about it that way without a connection to the others. So the one that I prefer, as crazy as it sounds, is logit, our new best friend. Beta 0 is the expected logit, log of the odds of a probability of a 1, when x1 and x2 are 0. Beta 1 is the change in the logit per unit change in x1. Beta 2, change in the logit per unit change in x2. The end. It's nice and easy. Linear predictor, everything works the same way. It's a linear model. It's slope times variable plus slope times variable. All cool. Now there's only one problem. You might be saying to yourself, but what the hell's a logit? Like you'll end up with like, my logit is 2.4. Is that a lot? Like I don't, Well, if I say it's 2.4, you at least know one thing. If it's positive, that means what? It means a probability above 0.5. A probability below 0.5 would be a negative number. But yes, logits, like if you try to make a plot in a talk or a results section where the y-axis is logits, reviewer 3 is going to have a field day. You're like, what the hell is that? Touché. So some people try to fix it by taking the log off of it, and now you're back to odds. And so it's E to the model. And these things are multiplicative instead, which I can't handle. I just can't handle it. Like my head blows up. I hate odds. And odds are still hard to interpret in the sense that everything from a probability of 0 to 0.5 is shoved into 0 and 1, between 0 and 1, and a probability of 0.5 or higher is 1 to infinity. My mind can't handle that. I'll just be honest with you. But odds and odds ratios are very big in some fields, which is why I have to present it. And then there's probability. The y side is the most intuitive. If you have a y-axis on a plot that says probability, people know what that means. Nice and comfy. But now, how do I talk about what this slope is? A 1 unit, no. Exactly, that face, Terry. Like, no, you can't say what any of these numbers does, right? They're all embedded in these exponents and it's all crazy. So, yeah, question?
Is that what I feel like I've read this before, where they'll give you like a hypothetical scenario between like 2 pieces or something? Is that when they talk about probability? So they don't talk about the slopes per se, but they're like, give like examples.
Yes. That's a nice segue into what I was just going to say. What I tend to do is talk about the model coefficients in terms of logits, because that's a nice familiar 1 unit change sort of language. But then when showing what the model says, what it predicts, you calculate probabilities for prototypical values and you make pictures or comparisons. Then it's like, for example, If x1 is 2 and x2 is 4, then the probability of a 1 is blah. So going back and forth across these things is going to be very helpful. By the way, people who've taken item response theory, which predicts the probability of a correct response in binary outcomes, those models are all written like this in probability. So understanding that this is all the same thing is very helpful because each author will choose one of these three metrics to write their formulas in. By the way, this is one of those things, I'm very bad at rearranging equations and like simplifying and stuff. At one point I was good at it, but that was like 20 years ago and it's like gone now, maybe 25. Yeah, 25 years ago. But this is the same. So if you take the whole model and throw a -1 on it in the bottom, then you can get away with just having 1 in the top. So when you're writing out this model, say in SAS or something to where you want to save characters, sometimes people write it this way because it's faster. But this and this, both of these expressions for probability are equivalent. So here's how not to screw this up. Are you listening? Okay, this is tricky. And I made this new slide just for this because I thought it might be helpful, and I'll have to see if it is. Because it's real easy to do operations on these numbers that make no sense at all. So if what you're talking about, what you're trying to explain to somebody is a conditional mean, meaning what does the model predict? In general linear modeling land, we usually talk about that as y hat. In your textbook, they switch to mu. It's not like population mean versus sample, it's just another letter. So just because, right? Job security. So I'm trying to link these together. So if what you're trying to talk about is a predicted outcome for a certain kind of person, then you could express that in logits. You could unlog that prediction to express it as an odds. So then it's the probability of a 1 relative to the probability of a 0. You could do that. It's not often, but you could. Or you could unlogit it all the way back down from logits to probability, skipping odds. So link is how you get from probability to logits. Inverse link, what I call unlogit, is how you go from logits back down to probability. So you can do either of those things where this, right here, this log function, that's my link. This is how you unlog it. It's e to the predicted outcome over 1 plus e to the predicted outcome. Cool. Now here comes the tricky part. Slopes. You can take a slope that predicts in logits. If you exponentiate it, e to the, that slope becomes an odds ratio. That is an effect size for these models. And I think I have a slide coming up on that. Maybe? I had one. Where did it go? I swear I did. Maybe it's later. I don't know. I have like this vision of a slide I made and now it's gone. So it means it's elsewhere or maybe I just accidentally deleted it. But I had an odds ratio. Anyway, e to the. This is an effect size that is commonly reported to go with the coefficients. In Stata and in SAS, you can ask for them to do this for you. You don't have to actually get your calculator out, and I recommend that you don't. Because the software will also give you like standard errors and confidence intervals and stuff that go with it that your calculator doesn't do as nicely. But this is the part that people screw up. You cannot all the way unlogit a slope back down to probability. The reason that you can't do that is this picture right here. A 1 unit change in logits does not correspond to any equal change in probability. How big of a change in probability a change in a logit corresponds to depends on where you are. So if I'm going from a logit of 3 to 4, I'm going from a probability of 0.95 to like 0.97 or something, right? A tiny change in probability, even though it's a 1 unit change in logit. If I'm going from a logit of 0 to 1, that's a big jump in probability. Shown differently, come back here, where's my, this picture. The same idea. the effect of a variable matters less the closer you get to a predicted outcome of 1 or 0. That's just what it means. It can't matter the same because the scale is running out of room. So when you talk about a slope, it's a 1 unit change in the logit. You cannot unlogit a slope to talk about changes in probability. You can unlog it to talk about odds ratios. Yes, go back to
So
that.
can you give me an example of how you would talk about the effect size? Would you use just one slope unlogged, or would you use both? Or?
I would, and you'll see this in the example that we're going to do.
Okay.
I would talk about the point estimate in logits, and then in parentheses say odds ratio equals.
Gotcha.
That's probably how I would do it. Somebody else who's more comfortable with odds might do that opposite, like they'd focus on the odds ratio. I just hate odds.
Gotcha.
I just hate them. I don't like it. It doesn't make sense to me. I don't like how it's asymmetric. Because if I look at an odds of like 0.2, it's like, well, is that a lot? Like, because it can only go to 0. Whereas like you can have the same odds ratio if you flip 1 over 0.2. Someone get their calculator out. Like, what is 1 over 0.2? It's a big number, right? But that number is the same. And that I can't handle. I can't handle the asymmetry. So I don't do odds, but a lot of people do. But so you can unlog your slope. You cannot unlogit it back to probability. All right. Let me... okay. So if that wasn't fun enough, I want to introduce you to another version of an intercept that software will provide for you against your will. And it will still be called intercept on your output, but that's not what it is. Welcome to the job security portion of the program. The term that is this intercept-like thing that's not an intercept is called a threshold. There's a long-running joke I make in the SEM class I teach using M+. M+ refers in its output to thresholds using dollar signs, like $1, $2, and I say like literally like someone will pay you if you understand this, and that's why they use $sign for this symbol. Thresholds is another way that you will get a version of an intercept. It is backwards. The idea of a threshold shows up when people who write the same model do so using a notation called Y star. Y star is supposed to be an underlying latent variable. That's all bullshit, okay? Like, you don't know what it was. All you have is a 0 and a 1. So I think my underlying variable that created my propensity to be a 1 follows this distribution. Okay, sure. No, I think it follows the normal instead. Okay, sure. We can't be right because we don't have the data. It's a scaling thing. But when people write the equation this way, E shows up again because what they're talking about is the variance of a distribution that underlies the binary response. And in this way of talking about it, they refer to something called a threshold, which is a cut point, where if you are greater than the threshold, your Y is 1. If you are less than the threshold, your Y is 0. It works out that -1 times your intercept is your threshold. So going back to this picture right here, it's this idea. Your software is either going to give you the logit that goes with the probability of a 1, that's the intercept, right? Because it's the higher value, it's the mean of the variable, or it's going to give you the logit of the probability of a 0, which is your threshold. If you are unhappy with having a threshold instead of a intercept, flip the sign. Then you get the other one. So there is a weirdness to thresholds, which is why I hate them not quite as much as odds, but up there. Because when you write your linear model equation, I'm back on slide 13 here, it's -1 times the threshold plus the rest of your model. meaning your whole model doesn't predict the probability of a 0, just the first part. The model becomes logically inconsistent. You end up with a beta 0-like parameter that gives you the probability of a 0 when all your x's are 0, but then the slopes of the x's predict a 1 instead. You'd think I'm making this up, but I'm not. And so step 1 in any analysis that I would recommend that you do is fit an empty model. Do you know what that word means? Empty meaning no predictors. Literally just fit whatever you think is an intercept and see what number comes back. You will see if it's giving you intercepts or thresholds. I, whenever possible, override the software to have intercepts, because then everything is predicting the probability of 1 in the same direction. The equation is internally consistent. Yes, ma'am?
So are there only 2 possible values for the threshold then?
A threshold can be any possible value because it's the cut point at which a 0 switches to 1. Like if you have like a propensity to be correct is your latent underlying and you only have yes or no. Right, at some point on this imaginary, right, y star is a bullshit imaginary construct because you don't have it. At some point on there, you switch from a 0 to a 1. And the threshold is that point. But the threshold is not an imaginary construct. It's just the logit of the probability of a 0.
Okay, so you were mentioning distribution before. Does it not automatically take on the Bernoulli since we specified?
Bernoulli is the distribution of y.
So not
This is the distribution of pretend y, y star. Excuse me, it's latent. Yeah. Yes, that face, yes. And people do simulation studies to argue about this. If the
It feels like
pretend,
it's just random.
you can't be wrong.
Yeah.
Like, you don't have it. You have a 0 or a 1. You can make up whatever story, like, led to that 0 or 1 you want, but you can't be wrong or right. But that difference in the pretend underlying distribution is the difference between 2 different kinds of regressions for binary data. If you're saying that your pretend underlying distribution is logistic, it looks sort of normal, but it's like flatter. Then you say, well, the variance of the logistic distribution works out to be 3.29. And that number becomes a proxy for what your model residual variance is in the model scale in Logit land. So you will see this 3.29 show up in calculations of R square, pseudo R square, and things like that. Because what you're trying to do here is predict in Logits, the variance that's left over in Logits is 3.29. But when you get all the way back down to the 0s and 1s that you have, they follow Bernoulli, because this doesn't exist. So if you pick a different one for your pretend underlying continuous distribution and a different link that does the same thing, now you've crossed over into probit regression. You heard of that one before? It's a thing. I think it actually came first, but it's mathematically like harder back when computers were like really crappy. And someone figured out that Logit is easier, and so that becomes more common. Probit regression does the exact same thing but using different scaling. The link function in a probit is not a logit, it's a z-score. The probit is the z-score that corresponds to the area to the left of a probability. Do you remember intro stat where there's like tables of z-scores and probabilities and areas and shit in the back? That's what I'm talking about. So if I have a probability of 50-50, that's a z-score 0, right in the middle. And you can figure out what the z-score is that goes with the area as you move over one way or the other, right? Where anything that is an area of less than 50-50 is a negative z-score, and then anything that moves to the right is positive. So z does the same thing as our friend Logit. It's continuous, it's symmetric, and it goes on forever and ever. So you could predict z, or you could predict Logit, and it does the same thing. It accomplishes the same goal. But the scale of the coefficients is different because probit goes with the idea that the pretend underlying distribution is normal, not logistic. And therefore, its variance should be 1, not 3.29. So it looks like if you run the same data, like the same predictors on the same outcome, through a logistic regression and then through a probit regression, you will get 2 different sets of numbers. However, should you care? Probably not. Probably means probably in my Midwestern vocabulary. I would also accept probably as an alternative, but probably is shorter. Probably not. So there is a mapping here of the pretend underlying distribution idea. Let's say that we have a threshold of 0, the point where a real score of 0 switches to a real score of 1 that corresponds to pretend la-la land on the x-axis here. If we're willing to believe that the distribution of pretend y star, is normal, then y star has a variance of 1. If we're willing to pretend that the pretend variable variance is logistic, or the distribution is logistic, then the variance is 3.29. And someone, again, way smarter than me, figured out that if you take your probit coefficients and multiply them by 1.7, you end up with Logit. And do you see these 2 curves right here? There's one black and one red. That's the difference in what is predicted by these models. So that is my conclusion. Is one better? No. They're the same thing to many decimal places except for very infrequent sections of the curve here. So why does this matter? You could just be like, well, I'm not going to do this probit thing. I'm just going to stick with Logit, right? Because one of the problems with probits is that to be able to go from a probit back to probability, you have to integrate. There's no easy formula. By the way, item response theory, folks, this is a normal ogive model. Probit is ogive. Logit is the rest of it. 1 parameter, 2 parameter, 3 parameter, 4. Logits are everywhere. So probits then and logits. Why do you need to know both of these? Why did I even do probit if I'm never going to use it? Because when we get to multivariate models like path analysis that has a binary outcome in it, certain links go with certain types of estimators. And if you use what's known as a limited information estimator for binary outcomes, it's the only thing that's available in Lavon and R, for instance. It's the default in M+. They insist that everything be probits. You don't get a choice. So anticipating that ahead of time and knowing, okay, this is just on a different scale, can help you try to make sense of what the coefficients are. In that case, they're predicting z-scores, not logits. Okay. How are we doing? Isn't this fun? Questions?
I just really don't like this threshold thing. So do you just ignore it in your publications? Like, how do you talk about it?
You fix it. So actually that is, let me see what else yeah. I'm going to segue right there. We're starting example 1. How do I fix it? This was like the last 2 or 3 days of my life, by the way, trying to fix this because I just can't accept thresholds. So I have an example that's not actually a binary outcome, but I made it that way for the first part of the example, and then we'll do a 3-category version. So Stata has something called Logit and O-Logit, and for the latter, they insist on thresholds instead of intercepts. It won't let you override it. And so I lost my mind trying to figure out how to fix this and stumbled across someone else's Stata package that they made that does intercepts instead. So it may take some digging to find software that doesn't use thresholds. It's a much more common thing in models for ordinal data than logistic. But knowing whether you're predicting the probability of a 0 or a 1, that's the first step to try and figuring out what your software is doing. So yeah, you can hate the threshold thing all you want. I'm right there. But the nice thing about it is that even if your software gives you thresholds, do you know how you fix it without having to find new software?
You just change it to a negative instead of the plus.
Yeah, you flip
Or
the sign.
positive to
You flip
it.
the sign and that's it. So yeah, I will report intercepts even if that's not what it gives me because people know what an intercept is. They don't know what a threshold is. And it doesn't make any sense to me to have the intercept of the model predict the 0 of a probability and the rest of the model predict a 1. That just, no. So let's see how to do this. So these are data that I borrowed from a website online. This UCLA place, by the way, they are a great repository for stats help. They have all kinds of examples of how to do things in various programs, and they also host a lot of data sets from textbooks. So this is a general place that I would recommend. This example has an outcome that I created that's binary of whether or not someone intends to apply to graduate school. We're going to predict it from their undergraduate GPA, whether or not at least one of their parents has a graduate degree, a yes or no variable, and whether or not they attended private school. So one of the things about these sorts of outcomes, odds are good, no pun intended, if you have a binary outcome that most of your predictors will be binary or categorical as well. So the examples that I'm giving you are going to sort of hone in on that as the most common case. There's nothing that keeps you from putting in continuous predictors instead. And GPA in this case is actually continuous. It ranges from just below 2 to 4 on a continuous scale. So it's bounded, but it's continuous. Enough. It has non-integer values, so by the way. The other thing that I'm trying to do here is, when possible, give you software options that you can use multivariate models on, not just univariate. So that's why for this example, I'm using what's going to be called ME Logit in Stata. That stands for Mixed Effects Logit. So you can have fixed and random effects or just fixed effects. The same thing with Glimix and SAS is what it's called when you're allowed to have generalized models with fixed and random effects if you want. So I'm using those for the example for today. So I have all of the files that go with this. Did I put them up? I'm trying to remember if I put them up. I don't think I have them up yet. I don't have the raw files up yet. I will fix that right after class. This we have up, but I don't have the raw files. I'm sorry, I forgot to do that earlier today. But you can see the full output in both programs. What I do for these handouts is just hit the important parts of the code, add notes, and then I paste in the output that we need to look at. So the full version of it you will have access to once I remember to put that up. But I'm going to show syntax in both Stata and SAS. The output that I show will probably be some mixture of both, depending on what is easier in either program. Your assignments for this class you can do using either program. You could probably do them using R as well, but I can't guarantee that you'll get the exact same estimates. In theory, you should, but it depends on the quality of estimation. So the name of the data set, as I downloaded it, is called OLogit. That stands for Ordinal Logit Models. I'm creating a new variable right here just for the purposes of having a binary outcome, okay? Don't do this to your data, all right? Never take your data and cut it up or put it into fewer categories, right? This is just a demo because I didn't have a binary outcome.
And this is in Stata.
This is in Stata,
Right.
yep. So what I'm doing is taking a variable that is called apply, and apply ranges for 0, 1, or 2. I'm saying I'm going to make a new version that's called apply 2, meaning 2 categories, and if the value was, this new variable is going to become a 1 if the original value of the variable was 1 or 2. So I'm keeping the zeros and I'm collapsing the 1s and 2s together. So the new categories that I'm assigning this is, are you going to apply to grad school? 0 is no, and 1 means, pry. It's a collapse of maybe and yes for right now. We'll split it out in the next part of this example. Otherwise, I have labels on here that tell you what these variables mean. So we have parent GD stands for graduate degree, 0 is no degree, 1 is yes, and then we also have a new variable called private, whether or not they go to private school, where 0 means no, they go to public school, and 1 means private. And here is how you would get descriptive statistics. Here is the corresponding SAS code to do all of those things. I also center GPA at 3, which is near the middle of that variable, since a GPA of 0 is logically impossible. Okay, so most of this type of coding variables, adding value labels and variable labels you would have seen before in an earlier class. Does any of this not look familiar that you want me to talk about? Either in SAS or in Stata? No, we're good? Okay, yeah, don't hesitate to ask if you see something that looks unfamiliar. The other thing that I'm trying to do in my handouts, here is this sentence starts a log file in Stata that sends all of your output to a separate document that will have a .log extension, which is just a simple text file, so that you can open it and look at it outside of Stata. The equivalent in SAS, I'm generating a rich text file right here to do the same thing. So that way you have a record of all of your output that you can look at without having access to the program. First thing, let's do some descriptive statistics, get to know our variables. So the mean of GPA is exactly 3. What are the odds? I think this data is fake. It ranges from 1.9 to 4. The crosstabs of whether or not they go to public school or private school versus whether or not at least one parent has a graduate degree. There are very few people in public school whose parents have a graduate degree. So we'll keep this in mind in terms of our precision of prediction for that kind of cell. Most of the people in this fake sample go to private school, but their parents do not have a graduate degree. And then in terms of the binary outcome that we're predicting, 55% of the sample said, no, I'm not going to apply to graduate school. 45% said at least, or yes. So I'm collapsing this maybe and yes variable into something that is at least a positive response. So 1 means they're at least somewhat likely to apply. Yeah?
Is there a specific amount of yeses that you would need?
If your variable is basically a constant, you can't predict a constant. Anything other than that,
Basically a constant. What does that mean?
another nice segue. I put up an article for you that is Logistic Regression power tables. Let me just dissuade all of you from ever having binary outcomes. Right? Just don't do it to yourself, of course. Adobe really wants me to spend my money to know it. So this is from 1989, so it's a little bit dated, but I have no reason to believe that it's not wrong, or that it's wrong, I mean. So let me answer that question. So this is a table required for a univariate logistic regression given the overall proportion of zeros or ones, like how much of a constant are you trying to predict, and odds ratios as your effect sizes. And this is alpha of 0.05. Okay. So an odds ratio, the further from 1 you are, the smaller the effect. So like this distinction right here, that's just straddling like a tiny effect, where going less than 1 is a negative effect. If you take the reciprocal of it, you get the odds ratio into positive land. Okay, so if you have a 50-50 probability, 50% ones, 50% zeros, that's your best case scenario. Even in that best case scenario, your sample size ranges from 2,000 people to have a small effect, down to, if you have an odds ratio of 3, you only need 50. Watch what happens as you move up this table. The further from an even split you have, the harder it is to find an effect. If you want to find a very small effect, and you have basically a constant but not completely, 1%, you need 52,000 people to have decent power for that. So you can try. The other thing that you may run into is what's known as It's empty cells, but there's a special term for it that they talk about in your textbook. One of the reasons why I wanted to check this, you can end up with cells that are empty when crossed with the answer. Like there's nobody who answered 0 that's in a certain cell, and then it can't like come up with an effect that involves that cell. When that happens, you will see standard errors that go to like 5,000 or something. Like it will just like you'll have output that looks crazy if it doesn't warn you about it explicitly. So yeah, does that answer your question? Yeah, you got to have the same as in regular regression, some kind of effect size that you're trying to power. But the other thing that you don't usually have to worry about is this p column. How much of a constant versus a variable you're trying to predict. That matters. So, all right. So step number 1, figure out what the hell your software's doing. That's step 1. That means, am I predicting the probability of a 0 or a 1? So in terms of my equation, this is what it looks like. An empty model. All I have is beta 0. So it should spit back the probability of a 1 if what I have is an intercept, and it should spit back the probability of a 0 if what I have is a threshold. And how do I go from logits to probabilities? It's e to the prediction, the logit, over 1 plus e to the logit. So in Stata, I'm adding titles to the output here as display as. That corresponds to the title in SAS, same function. ME logit is the routine that I'm using. That stands for mixed effects logit. Apply to is the DV. There's nothing after it, meaning I have no predictors. SStat is what's used to calculate AIC and BIC. You can ask for that. We haven't talked about what those mean yet, but that's extra piece of information, and I gave it the sample size so that its calculations would match those of SAS. And NLCOM is something you may not have seen before. Have you guys seen this one? It's nonlinear lincom. So it's how you can ask for linear combinations of model parameters that are actually nonlinear. So what this is doing, this underscore b const thing, that's internal Stata code for what it calls the constant. I don't even remember how I found this, but it took some digging. That's what I remember. So what I am doing here, this equation matches this thing right here. It's just that I wrote it the short way, where I take -1 times the predictive part and 1 over that. So I wrote it in terms of this, the bottom one here. That's what it is. So I'm just asking Stata to generate a probability for me. It gets much easier once you have predictors in the model, by the way. In SAS, this method equals, that stands for maximum likelihood. It's not a default in all cases, and so I include it here. It is what's going on in Stata. I don't know that there's anything else that you can ask for unless you specify. ME logit you can, and regular logit you can't, excuse me. In SAS, the model line looks exactly like what it does in general linear models that you've seen. It's model, outcome, and then this keyword descending. Do you know why that is? Because Glimix by default gives me thresholds. And I figured out that that's how you force it to have intercepts instead. Right here is where the predictors would be if we had any. We don't. Solution means give me the fixed effects estimates. That's not a default, believe it or not. And then this last part, this is new. Can you guess what link equals logit does? Yeah, it makes our new friend logit as what's being predicted. And distribution equals? Yeah, it's binary. Do you know what the default in Glimix is? Not this. Here, I'll show you real quick what the default is. That's the default. What do I get if I forget to change it from the default? What do you know of as an identity link with a normal distribution? Regular regression, yeah. An empty general linear model. So even though I'm running this special generalized linear models routine, the default is the regular general model. Who knew? Job security. So make sure you know what you're looking for. That you have these things on here to tell it what to do. Estimate in SAS is how you request linear combinations of parameters. In this case, the reason that I'm writing this is because of the keyword after this. Can you guess what ilink stands for? And feel free to read from the screen, you know. Inverse link function. That's how you unlogit predictions down to probability. It does it for you. Okay. How are we doing so far? Yeah.
Can you explain what in Stata what the difference again is between any Logit and Logit?
Logit is for single level univariate models where the cases are supposed to be independent. ME Logit is mixed effects Logit that allows you the option to add the multi-level part. I don't have any random effects in here, so this simplifies to Logit. This is functionally Logit. I just picked this because later in the semester I'm hoping to do multivariate models where we'd have to use this one instead. Same thing with Glimmix. You could do proc logistic, and that would be a single level version. Glimmix is for mixed effects models that have both, but if I don't have any random effects, then it's just single level. Good questions. So SAS spits out this very unhelpful table right here that tries to explain what it's doing, which makes no sense to me. But then I see this sentence, and that makes me happy. It is modeling the probability that apply equals pry. That means we're predicting the one, we have intercepts. Hooray.
Wait, can I ask a question? So
Yeah.
how do you know that from Stata which one's predicted?
Yeah, because this estimate right here,
Since it's a negative?
negative, means that it corresponds to a probability of less than 50-50, and because I have the data, I know which one it's giving me.
So it takes a little longer.
A little more work, but these percentages should come back if it's correct. So Stata is predicting the logit of a 1 because that logit corresponds to a probability of 0.45. So in SAS, I say here, we haven't talked about log likelihood, but just so you know, log likelihood is what SAS spits out at the end of its iteration history. It takes it times -2 to put it here. Stata will only give you log likelihood. So it's taller is better in log likelihood, smaller is better in -2 log likelihood. For now, we're not going to use these numbers for anything. They'll show up later, but not now. The parameter estimates. So this is where it would say constant in Stata. It says intercept in SAS. -0.2. That's a logit. It's the log of the odds of the probability of a 1. This standard error corresponds to this logit. So this is like the standard error of the mean in logits. Estimate divided by standard error is this t-value, as usual. And with denominator degrees of freedom of 399, that corresponds to this p-value of p less than 0.05. Hooray! Oh, wait. Do I care about this? It means my mean is different than 50-50. Maybe I could care about that, but not today. The estimates that I requested on this right here, that's the next table down. And SAS does not make this easy on you. The first part of the table repeats logits. So this is redundant. Logit, intercept, its standard error, degrees of freedom, t, p. The reason I asked for this is the last 2 columns. Mean. Mean what? You have to know what the inverse link function does to know what metric that is. It doesn't change the label based on what the number means. I know, right? This is a probability. And that is the standard error of the probability. So this is why it's helpful to be able to ask the software to do these things, because then if you needed to make a plot and have like error bars, you would have the standard error bars that go with it. And Stata will give you probabilities as well. That's what the NLCOM sentence did.
Does Stata change the labels?
Yes. It has, here, let me show you what it's going to look like. So this is the next model that we'll do next time that has 3 predictors in it. And I have margins right here in Stata that generates predicted outcomes. So I have to tell it, what is my scale of predicted outcomes, right? Do I want logits or probabilities? If I say predict XB, it's in logits. If I say nothing, it's probabilities. Logits will not be labeled, but probabilities will be. So the one that's not labeled is the one that actually corresponds to the model. The one that is labeled is the one that you ask for extra, and it's the default. Yeah, all this fun stuff. But yeah. Now this part, doesn't this look like nice and familiar? Yeah, it's just the rest of it that's all crazy. That part is going to be the same so long as we're talking about logits. All right. Good for today? All right, questions? So we're going to do predict binary outcomes. We can't predict them directly because the probability is bounded, but we're going to predict it with a link, like a logit or a z-score. And we're going to say the binary outcome has a Bernoulli conditional distribution. And then we do our regression just like normal. Okay? All right. I will send you an email as soon as your first formative assessment is up. Those are not software program problems. They're just review questions. Please try to get it done by Monday night. That way I can read the answers on Tuesday and we'll go over it in class. I'll also let you know when your homework is ready. So, all right. Have a good rest of your day. Have a good weekend. Feel better, those of you who are sick. Hang in there.